Hello, everybody. My name is Anoushka Chaudhury, and I'm in the 11th grade in the International School Bangalore TISP in India. For my project, I coded up a quantum circuit simulator using Python with my mentor Ben. It sounds complicated, I know, but it's really, in simple terms, a system that tracks the backend math at each stage of processing by a computer. I chose this topic because it combines my passions for coding and math, and I wanted to understand why and how quantum computers can process information so much faster than the classical computers we use every day. I thought the best way to do this was to build a simulator myself that does the backend calculations, making use of Python libraries to handle complex numbers and linear algebra. Basically, how computers work is each piece of information undergoes algorithmic change in a computer as it gets processed. This processing changes the value of qubits, which is information stored in classical computers, in the form of zeros and ones. Quantum computers, however, utilize quantum superposition, which allow the value of qubits, which are quantum bits, to have a value of 0, 1, or both at the same time. These computers also make use of quantum entanglement, where the state of one qubit is directly connected to the state of another, no matter how far apart they are. So thanks to superposition and entanglement, qubits can exist in multiple states simultaneously. Therefore, quantum computers have the potential to perform computations in parallel, which contribute to their incredibly fast processing capabilities. But to get any useful information from quantum computers, we need to measure qubit values. The measurement of qubits is also called destructive measurement. This is simply because the state of the qubit could be anything, but all we know after measuring it is one specific value, which is a 0 or a 1. So it's destructive in the sense that it destroys information. The way that a quantum computer determines whether it's a 0 or a 1 is that it basically flips a coin according to the probabilities of getting a 0 and a 1 state respectively, and then outputs a single value. I understand conceptually it's a little unconventional. However, I'll show you what I mean by using a piece of my code. So in this short module of code, I'm generating a 3-qubit GHZ state. A GHZ state uses quantum entanglement to create a connection between states. A change to one qubit results to a change in another, which makes it useful during communication to send secure messages. In this next line, I'm measuring the qubit value with the index of 1. And here is the output of the GHZ state that we generated. The following piece of code shows that when we measure the GHZ state, it collapses to a value of 0 in binary terms when measured. So the state in this case is 000 due to 3 qubits. By running the same piece of code a couple more times, you can see that the output value is now a 1, the state becoming 111. This is how destructive measurement works. We can never recreate the exact original state again, and the measured output is very much like a coin flip. The applications of my project are quite great, especially since quantum computing is a rapidly growing field. My project could be invaluable for testing and refining quantum algorithms, as it can help developers understand how algorithms behave under different conditions, helping them optimize its performance and accuracy. It can also be used to test quantum algorithms before they're deployed on actual quantum hardware, which can be quite expensive. Since quantum systems are prone to errors, to noise, and decoherence, the simulator could help study error correction techniques and develop strategies for error mitigation to make quantum computers more reliable. With my coded simulator, I have built an error correction algorithm, which incorporates Shor's 9-qubit error correction algorithm as well. The algorithm encodes the state of a qubit in such a way that if an error is applied to one of the qubits, the original state can still be recovered. Classical computers check and operate on errors in a similar manner. However, Shor's algorithm is more specific to quantum information. The algorithm is broken down into 2 parts, encoding and decoding. During encoding, error detection is performed by applying certain operations known as stabilizer measurements, which provide information about the presence of errors in the system without directly measuring the state of the qubit. This is done to reduce the errors that may occur from destructive measurement. However, it does not directly reveal which qubits were altered. Instead, the structure of the decoding algorithm considers how applying an error to these different qubits will affect the state of the first qubit. Hence, following this logic, the decoding algorithm is applied to undo the effects of the errors and to restore the correct state. So that was a little theory intensive, but here's a more intuitive way of understanding how the algorithm works. Let's say we're trying to communicate the message Polygence fosters innovation, which is stored in the variable sent message. If an error is deliberately applied to the message without Shor's error correction algorithm, this is the output we get. It doesn't really make sense. However, when we do apply the error correction algorithm, inducing the same error, we can recover the original message. There are, however, some limitations to this algorithm, which I further explored using visualizations. So the expected ratio of the outcome for this algorithm is approximated to be 1 minus cos theta whole divided by 2. This plot shows the results when one error has been induced to a random qubit. The algorithm was able to correct the state, and hence the observed ratio meets the expected ratio. The slight deviation in the observed ratio is due to destructive measurements and distinct values of theta taken to create the plot. So the more theta values we use, the more accurate the observed ratio would be to the expected. However, on the right, we can see that the observed ratio is very noisy and distorted. In this case, 2 qubits were induced with errors. It shows that the error correction algorithm does not work when 2 qubits contain an error, which poses a limitation to the algorithm. In a similar manner, demos of other algorithms can be created, which could be invaluable in developing quantum computing systems. Thank you.